Thank you. Ladies and gentlemen, I invite you to think and imagine a future where there are as many quantum computers as there are classical computers, where there is as many quantum sensors as there are classical sensors. A future where wherever you find a CPU or a GPU, you also find a QPU on the same motherboard. Wherever you find a classical sensor, you find a quantum sensor which is fused with that classical sensor. That is a bigger future, a more diverse future, and a more impactful future for quantum technologies than is offered by many of the emerging approaches to building quantum technologies today. Many of those approaches are limited because they are either large, they require cryogenic cooling or vacuums, or they have fragile systems that must be kept incredibly stable. To build that more bigger and diverse and impactful future, we need a technology building block for quantum technologies that is analogous to the silicon transistor for classical microelectronics. That building block needs to be microscopic, it needs to be reproducible and manufacturable, and it needs to be able to be configured in different architectures to produce different device functionality, such as sensors or purpose-integrated circuits to deliver a certain logic function, or even processors to process information. So the fact is that we have known what that building block is for quantum technology for some time. And that building block has been the nitrogen vacancy center in diamond, which is an exquisite qubit system in diamond and one which is employed already in many quantum technologies. So let me introduce what the nitrogen vacancy center is in greater detail. So it's an atomic defect in diamond, and to date it has shown these exquisite properties of coherence times greater than milliseconds at room temperature, and that's a regular phenomenon, not an unusual phenomenon. That you can achieve 1 and 2 qubit gate operations, as well as initialization and readout fidelities greater than 99%, and that you can do this fast. You can do this on the megahertz timescale. And when you cool this down for specific applications, you then have a coherent photon interface for your qubit, which allows you to do loophole-free Bell tests over kilometers and to exchange and entangle different distant qubits. So that's this exquisite property of the nitrogen vacancy center, but that isn't all the conditions that we need for an analog to the classical transistor. You also need the ability to configure it in different device configurations, to be able to use it adaptively to create different device types and to be able to manufacture it. And to have all the other systems that go around it to also be manufacturable. Now, diamond ticks those boxes, but the challenge has been around how to manufacture it reliably and with greatest precision, and how to then fabricate those integrated devices like we see for classical transistors. And so that challenge is the challenge that Quantum Brilliance is addressing, and I'll talk more about that as I go through my presentation. But let me further introduce diamond quantum technologies. So to date, there is over 40 companies worldwide who are building diamond-based quantum technologies. They're doing it across a diverse set of applications ranging through sensing, computing, and communications. And these companies are large corporations right through to small startups. What you can see there on the right-hand side is already there is a variety of prototype devices or even pre-production products. These range from the Raspberry Pi-sized magnetometer that Bosch has produced at the top, through to things like a magnetocardiogram that Sandbox has produced, as well as semiconductor inspection tools. And in the middle there, you see the completely room temperature 19-inch rack quantum computer that Quantum Brilliance has developed today. Further below, you see alternate quantum computing technologies, such as the cryogenic version being developed by Fujitsu and TU Delft. And finally, photonic repeaters, such as those being produced by LightSync and also pursued in Delft. So, having something which can be miniaturized, something that operates entirely at room temperature, that has diverse functionality, leads to applications which are mass deployable. And so let me give some examples of mass applications. One of them is in positioning for navigation etc., without GPS. And so using a precision magnetometer to measure your local magnetic field and to compare this against a magnetic map to provide a positional reference to update other navigation systems. So what you can see on the bottom is results obtained by Phaser Quantum in Australia, which is a diamond quantum sensing company, where they demonstrated positional accuracy of better than 100 meters for a US military flight across the Pacific. So this is a technology that lives today, that's the size of a mobile phone, that is delivering real performance in being able to navigate without GPS. And so it's a very exciting moment, that demonstration. On the right-hand side, we see what's the potential of having a quantum computer the same size of a GPU. So here is specifically in the application of quantum machine learning. Here you have hundreds of these GPU-sized quantum processors doing training in a data center. A real bottleneck for quantum machine learning applications, and the advantage here is the parallelism that many parallel quantum processors give you to that training. And then the deployment of those quantum processors to the edge, say in satellites, performing synthetic aperture radar image inferencing, in order to perform that inferencing at the edge, to really deploy that machine learning to its full capability. Now, the common key to make all of this happen is the development of an integrated quantum chip. So that's a device that combines the diamond with those nitrogen vacancy centers, being the qubits within it, with the electro-optics that actually drive and control those qubits, and the magnetics that stabilize those qubits in a packaged device that will one day be the same size as integrated chips that you see today. So this is who Quantum Brilliance is. This is what we do. Our job is to develop and deliver these integrated quantum chips for diamond quantum technologies so that people can use these to build sensors and to build computers now and into the future. So we did a lot of work across the diamond quantum technology community over the last year. And what we did is we sought to create a common roadmap for integrated quantum chips for people to participate, support, to be able to plan and understand, and also tell us what they need. And some of the high-level conclusions from that work we did with the community was categorized as 3 generations or 3 types of integrated quantum chips that we will evolve through into the future. So we're currently in type 1, our first generation. That's employing currently accessible materials and device structures to deliver basic functional performance, like Phaser Quantum with their device that they've used in magnetic navigation, and like our 19-interact quantum computers that we've used to demonstrate basic quantum computing. Where we need to go to next is a generation 2 chip. So that's a chip that employs primarily the introduction of new electronic control and readout into the diamond, as well as new photonic elements in order to take what is relatively basic electro-optics into a more advanced form that allows higher performance, but more importantly, something which is manufacturable. We're using electrical contacts instead of only optical interfaces that enable you to scale a more reliable device that achieves higher performance. That requires innovation on the material side, as well as those electro-optical interconnects. And then finally, generation 3 is where we take that developed in generation 2 and we now take it to the nanometer length scale. So we're reducing our node size to something where we have nanometer precision over the placement of those qubits and nanometer precision over our fabrication of those electrodes. And we do other things like including multiplexing, etc., to be able to have multiple channels to, say, scale up the number of qubits that can be addressed. And so as we go through those device generations, we see this switch from enabling basic sensing applications into more advanced sensing applications, and then eventually into computing and communication devices. The key message we have in this presentation is that Quantum Brilliance holds the key for these core component processors. But we need to work with the semiconductor value chain in order to bring all of this together to be able to manufacture these integrated quantum chips. So Quantum Brilliance will integrate with the semiconductor value chain, bringing these core process technologies and designs with established semiconductor processes to develop and deliver these chips. What are some of the implications of these deliveries? So in that generation 2 device, so that next device which quantum brilliance will enable, there are some key inputs that will deliver. A step change in the quality of the diamond and a switch to a new type of diamond to be exploited in devices, which is known as the 111 orientated diamond. The introduction of N and P type functionality to the diamond to enable the stabilization of the qubits, as well as the introduction of photoelectrical readout, that thing that enables higher performance and also higher manufacturability of these devices at that performance level. And those factors combined, we can show, will give a 10 to 100 times improvement in, say, the sensitivity of the device. So let me talk a little bit more about quantum brilliance. So quantum brilliance was founded in 2019. It was founded with intellectual property developed at the Australian National University, as well as the University of Stuttgart in Germany. Since then, we have grown into a company of 90 plus employees, which is roughly half distributed in Australia and in Germany. We have offices across those countries, but as well as United Kingdom, and what I'll talk about later, in Japan. The character of our different sites is that in Australia, Canberra is where we do the production of our current generation of quantum computers. Melbourne is where we're creating a new venture, which is called the Quantum Diamond Foundry. Its role is to work with suppliers, say in Japan, in order to produce the diamond that's required for these quantum diamond technologies. In Germany, our locations are in Stuttgart and Freiburg, and this is where we were working as part of the European ecosystem to develop those integrated devices, to solve and deliver the processing as well as the design of those electro-optical interconnects with the diamonds which are otherwise being produced by Australia and its supply partners. Here is just a selection of the partners and customers that we have, as well as the various investors that we have, which include investors across Australia, Japan, Europe, and the US, and notably sovereign wealth funds in Australia. And that really gives us the ability to think long-term and to develop sovereign industry capability in those various nations. So over the last 6 years, we've developed 3 capabilities. So one capability is an advanced diamond synthesis. So those novel processes that will enable us to deliver those type 2 devices and then set the conditions to develop type 3 devices, as well as integrated device development, so those micro and nano electro-optics, and being able to build those into fully integrated systems, such as the small-scale quantum computers that we currently deliver to people. And within those core capabilities, the intellectual property we've developed, that thing that enables us to be able to enable the integrated quantum chip, are the following. So I've talked a little bit about the advanced diamond that we're producing. The next is the ability to place nitrogen vacancy centers with atomic precision. And this, what you see on the screen there, is an STM image of the diamond surface where individual hydrogens have been removed from that surface at a 5 nanometer pitch. And that is an advanced lithography technique, which is the core enabler for us to be able to position nitrogen and their nitrogen vacancy centers in that diamond with atomic level precision at 5 nanometer pitches. Looking further to the right, we have developed the ability to simulate these integrated diamond devices, which is what then really enables the design of the integrated chips and the processes that are really needed to give them, as well as prediction of the performance of these devices. Next is our photoelectrical and nanoelectronic capabilities, which is our core ability to be able to increase the performance and the manufacturability of devices and onwards through our microelectronics and system design integration. So if I talk a little bit about our achievements in that last one, so the system design integration. So as far as we understand, we were the first quantum computing company to actually deliver a quantum computer integrated into a high-performance computing center and run hybrid computation back in 2022. In 2023, we did an interesting set of experiments where we drove our quantum computer out into the Australian outback and we performed quantum computing outside, powered by an electric vehicle. In 2025, we've exported our quantum computers to Germany, and we're going to undertake a very interesting deployment of a cluster of 3 hybrid computing units to Oak Ridge National Labs. So this cluster, each quantum computing unit contains a CPU, a GPU, and a QPU, and those 3 clusters are then connected together as a parallel hybrid compute system. Oak Ridge National Labs are going to use that compute system to pioneer methods for hybrid computing, as well as work with us to architect the future of what massively parallelized and hybrid computing systems will look like. We've also gained a contract from the German Cybersecurity Agency to deliver them what we aim to be the world's first mobile compact quantum computer in 2028 to support various national security applications. And so in terms of our chip roadmap, we now turn to the future now to really focus on the development of those chip scale devices. And so what we'll be communicating later this year is the demonstration of those core processes, which are the building blocks for building these integrated devices in Diamond, as well as a design tool that will enable people to design how to use those building blocks to create a variety of devices. 2026 is then our demonstration of how to combine them together in a scalable architecture for quantum computing, as well as our first Type 2 sensing chips. That will also be where our production of new material, which can also support the development of quantum sensors, will begin. 27 through 28 and onwards is then further miniaturization to system in package scale, and then finally system on chip scale in 2028 and beyond. Now, as I've said, what's very important to us is to be able to work with the semiconductor value chain, to those who are producing tools or materials. And in Japan, we've, for a long time now, identified a variety of critical partners in industry and academia that will allow us to uplift the quality and scale of Diamond, as well as those tools that will enable us to process a Diamond to implement those things that I've described. And as a result, I'm very pleased to announce today that we've incorporated in Japan to be able to drive those partnerships forward. And so we have Hideaki Yoshimura, who was our representative here, and so your point of contact to talk to in the Japanese community. And if you want to take action now and to do something, I invite you to download our virtual QPU, which is a fully self-contained emulator of our current and future quantum computers, in a way that you can use it to test what does parallelization of quantum computing mean, and a way that you can explore what does edge applications of quantum computing mean, as well as other opportunities that come to us and to start practically on understanding quantum sensing applications and the matches between different device types and those sensing applications. So with that, I'll end and thank you.